I should also say one goal is for this to be relatively informal. So if people have questions or comments, don't hesitate to chime in. We really want to have a conversation here. Okay, so with that, I'll let David take the stage.
So in Lars's defense, my original title is submitted had the two reversed from what's up there, but when I wrote the talks, it made a lot more sense to do it this way. So, Lars, you weren't wrong. But I did want to ask, does that mean that other evenings we can't go to a pub for a beer? Only the night we get off early?
I didn't mean to imply that.
Just go early on that day.
Even earlier. Okay, so my two talks today focus on this topic of reaction and stress-driven melt segregation, and that the idea is talking about how in the Earth you can channelize melt from porous flow into more channelized flow of melt, and it's really from the experimentalist point of view. So the first is to say something about the perspective. I once wanted to use this title, Frog's Eye View, with a paper with Greg Hirth, and he refused to do it. And I wrote a lot of jokes I could think about making about that, which I'm not going to do. But the earth science perspective is often to stand back and look at what's happening at a large scale. What's happening in mantle convection, molten building, and large scale processes. And for me, much of what we do is not looking at the forest from an airplane or from a bird carrying a camera, but is to kind of drill down and look more closely, maybe being the frog sitting on top of the leaf, seeing in more detail what happens. The idea that if you can understand what's happening kind of at the micro scale, you can hopefully apply that to understanding what's happening at the macro scale so that we have a good underlying physical understanding of sort of macro scale processes. That's the title. Okay, so when melting occurs in the Earth, it's thought to start fairly deep, 100 kilometers or so, maybe a bit deeper, maybe a little bit more shallow. Here is shown beneath a mid-ocean ridge, and in this all right. Now I see why using two screens is confusing. All right, so when melting starts, it starts at the grain scale, and so the initial melting that you expect to have move is going to move by porous flow, where the melt is really in intimate contact with the grains. And one would expect in that case that you would have relatively good chemical equilibrium between the melt and the grains. But it's quite clear from geochemical evidence that melt must at some point flow more quickly than by porous flow. You have radioactive uranium series constraints on the timing, and porous flow wouldn't bring melt to the surface nearly quickly enough. And also, when the melt arrives at the surface, it's out of equilibrium at the kind of major element level with the rocks through which it traveled. So someplace there has to be some channelized flow, and this is primarily what I'm going to talk about today, is the region where the melt moves from being under porous flow into some sort of channelized flow. And there are sort of two aspects to it. This first talk is going to talk about where chemical reactions between the melt and the rock through which it's traveling take place and help open up channels. And the second part is going to focus on what deformation can do to help localize melt into channels that have high permeability, provide fast pathways to move melt from down here toward the surface. And what I'm not going to talk about is kind of the last stage of brittle fracturing, where you have melt moving through dikes. I'm going to focus most of my attention down here with a little bit of talk about the porous flow region. Okay, so this is a figure from a paper by Rich Katz and Sam Weatherly, where they sort of show localization of melt. And in this paper, they address the difficulty of getting channelized flow unless they had some sort of heterogeneities in the mantle. I'm not really going to focus on it, but it's a pretty picture, and I thought it was a nice place to kind of start the conversation about it. So there are some geochemical constraints. The composition of the melt is out of equilibrium with the rocks through which it's traveling, which says that there has to be some kind of channelized flow. And so we're going to talk about these pathways or channels that localize melt to a mid-ocean ridge. And then there's isotopic disequilibrium, which gives us some constraint on the velocities, and the melts have to come up at a meter or faster per year. And to get the high velocities, there have to be, you simply can't do it by porous flow, so there has to be some channelization or high permeability paths. Okay, so there's field evidence that says that there's melt channelization. This is some work from Mike Brown and Peter Kellerman in the Oman ophiolite, and somewhere one of them is standing here. I can never see it when I give the talk, but there's a scale. So this is a hillside behind Muscat, the capital of Oman. And what you're seeing are these dunite layers, the lighter layers, kind of anastomosing through the darker layers, which are Hartsvigite. And in this particular outcrop, you don't see the larzolite, but you can in places also see the larzolite, which is the main rock in the mantle through which the melt has to move. So the dunite, for the non-geologist, is basically all one mineral, olivine. And the Hartsvigite, it has at least two phases. It has olivine plus pyroxene. And when the melt comes through, it's undersaturated in pyroxene, and so it eats the pyroxene out of the rock, leaving behind a dunite channel with all the pyroxenes removed. And you're left with a 2 or 3 or 4 phase rock here where the melt has not yet been able to saturate. So these are thought to be the channels. They're tabular in format, that is, they're plate-like or planar, roughly planar. You can think about them going into the screen here. And here's at a smaller scale from some of Seth Kruckenberg's work in the Twin Sisters complex, and where you see the same kind of structure at a micro scale. You see the brown color is the dunite, and the Hartsvigite, or the Hartsvigite, and the dunite channels are these small channels cutting through. So you can see that there's at multiple scales. Even here, you can see that there are some that are, tens of meters across, and then there are much finer channels in here, and it scales down to this sort of level. Okay, so just to put this again, I assume there are some people here who aren't geologists who maybe don't know quite so much about the rocks that we're going to be talking about, but the Hartsvigite again is here. It's composed of olivine plus pyroxene, and the dunite channels are here, and that's where the melt is thought to have gone through, removing the pyroxene. This melt coming up from below, which is undersaturated in pyroxene, removes the pyroxene and leaves these, when there's melt in them, are relatively high permeability channels. The other observation that Peter Kellerman and Henry Dick made back in the mid-1990s already was that these channels are also shear zones. So the second talk, I'm going to go from talking about the reactions being important in terms of removing the pyroxene and focus on the role of deformation in helping to organize and affect the morphology of the channels that we see.
David,
Mm-hmm.
the observations is consistently that the channels are tabular.
Yeah.
You never see them in tubes.
So you're talking to a lab person, but there is the world expert. And
Okay.
They can be either tabular or completely irregular. The dunite can be pockets,
Yeah.
completely irregular shape, but no, never tubes.
okay, and that. Thank you. Okay, everybody heard that? They're never in tubes. Okay. And Andrea is much more knowledgeable at this than I am. I may look like I know what I'm talking about in this when we're talking about field stuff, but I rely on people that know a lot more. Okay, so the melting starts. It has to occur at the grain scale. It's well documented now by people like Ulrich Fahl, who's done a lot of work in this area, looking at melt distribution. And to kind of a first order or maybe a 0th order description, when melt begins to form, even at a 0.1% level, the melt doesn't wet the grain boundaries in general, but it does wet all of the triple junctions. Okay, so all these regions that go between 3 different grains, so like I'm trying to show in the sketch here, and if melt gets on the grain boundaries, by and large it's a non-wetting fluid. There are some exceptions to that, but this broad generalization I think is fine for what we're trying to do. The flow is described primarily by just using Darcy's law, where we have the melt flux of the Darcy flux permeability driven by a pressure gradient, and then in the denominators there's the melt viscosity. Okay, so at least in the porous flow part you can make pretty good headway using Darcy law description of what's happening. Okay, but if the melt stays at this scale, and I think this is kind of the key observation, is that you would expect that the melt being in contact with, immediate contact with this grain, right? I mean, this grain is maybe a millimeter across, that you get pretty good chemical exchange between the melt and the solid. And what's observed is that that's not the case, that when the melt comes out, it's undersaturated in some of the components through which it's been traveling. Okay, all right. So, oh yeah, just to say with the permeability, since all these things are going to come up again, the permeability, we usually write it out in the form that it depends on the square of the grain size, and then some function of melt fraction, and that's usually melt fraction squared or melt fraction to the third power. And I think the most recent really nice experiments on this are some that come from Wen-Lu Zhu's group that have this exponent at being 2.6 based on. Maybe you're going to talk about this? Okay, so I'm not going to say any more about that. But this is what, in terms of what this talk has, when we did calculations, this is the relationship between permeability, melt fraction, and grain size that we used. Okay, so to get instabilities, these reaction infiltration instabilities, the idea is that we're taking a rock that starts melting at 100 kilometers depth, and in kind of gross simplification, it actually has two pyroxenes in it, plus olivine, and it produces melt. That is, the pyroxene gets dissolved into this melt and precipitates olivine back out. So that's the reaction we're going to look at. The idea, again, is that you have melting occurring at depth, and as the melt rises, it becomes more and more undersaturated in pyroxene, and so it wants to dissolve the pyroxene that's in the rock. And there's this positive feedback that occurs, that as you start to channelize the melt, the permeability changes. It becomes more permeable because you've increased the melt fraction there. That means more melt wants to flow into that region, and so it develops these finger-like and tube-like, as Gideon just pointed out, tube-like kind of structures that can rise then through the rock, kind of eating its way through the rock as it goes. So you're going to see this a lot. The samples we're going to use are going to be made up of pyroxene plus olivine plus a reactive melt, and what we'll find is that we make a new melt, and the pyroxene's been chewed up and leaves behind olivine. So that's the problem we're going to look at. And again, you can see the feedback that's involved here. Is if you think about studying this with Darcy flow, the permeability isn't a simple material parameter. It depends upon the amount of melt that's present. And if you have a reactive melt coming in, it makes more melt. And where that melt fraction is increased, the permeability goes up. And where the permeability goes up, the melt will flow into it. So you get this kind of positive feedback again that leads to these finger-like instability formation. Okay, and much of the way we design these experiments is to kind of following what some of the numerical people have done, like Mark Spiegelman and company primarily. But I've looked at two parameters primarily, the Domkohler number, which depends upon the rate of reaction, some length scale, fluid density, and then here the Darcy velocity. Okay, W is going to be just the melt flow velocity, so W is 0. Okay, and the second parameter in their consideration is the Peckley number, which depends upon the velocity of the melt in the channels, and a dispersion coefficient, which basically in the literature has been taken as basically the rate of diffusion of silica in the melt phase. So how rapidly tells you something about how rapidly this peak that's going in can grow to the sides, and it depends upon how fast the melt can be dispersed or diffusion in the melt phase to move it. Okay, and so there's been some numerical analyses done on this. This is work by Mark Spiegelman using two-phase flow theory, did calculations for reactive infiltration instabilities, and this is just meant to show you the influences of the Domkohler number and the Peckley number. And so you can see with increasing Peckley number, you initially get no channels, and at some point the channels nucleate, and the higher the Peckley number, the earlier they nucleate in the flow. And the same thing can be seen with the Domkohler number. And I'll come back to this later on, but if you look along this diagonal, which is basically a product of Peckley number times Dom-Kohler number that's equal to 1600, you'll see that the channel formation looks very similar along that particular line. Just at this end of it, it nucleates a bit later than it did in the flow up here. But I'll come back and mention that again in a few minutes. Okay, so trying to design experiments. This is kind of an interesting way to try to design experiments because it looks at first blush as if, well, there are all kinds of things you can control and change. You can control the reactivity of the system. You can control the pressure gradient in the system. You can control the rate at which the melt flows. You can change the melt chemistry and change the dispersion rate of the flow. And so you can, again, starting with Darcy's law, the permeability, you can see, well, if we want to change the permeability, and thus the flux in the system, you just simply have to change the grain size or the amount of melt in the initial sample, which are two things we did in fact change. And then you have all these other parameters you can change. Well, there's also the viscosity. Well, that's nice, but the viscosity depends upon temperature and upon composition. And you can change the reaction rate constant, which also depends on temperature, composition, and grain size. And you can change the rate of dispersion, which depends upon temperature and composition. So in principle, you've got this kind of bag full of things you can change. In practice, it's really hard to change one without changing everybody else. And so it makes the system more challenging than I think we thought at the outset. But I'll show you what we did and what parameters we've at this point been able to play with to kind of map out some part of Dom-Kohler-Peckley number space. Okay, so the first experiments that we did in this were done by Martha Daines back in the mid-1990s. And the basic idea is the sponge. You start with a melt, reactive melt, source down at the bottom, and then you have a rock made up of olivine plus pyroxene sitting above it, and you rely on capillarity. It's the sponge effect. You suck the melt with capillary forces into the sample. It dissolves part of the pyroxenes, and in this case, it actually makes channels. So this is from Martha's paper back in the 90s. Again, this is the system. There's no pressure gradient driving the melt. It's simply capillarity that drives the melt. And what she observed, at least in some cases, that the melt, which is down here, so here's the sample. This is the two-phase part. You can see the black pyroxene and the lighter phase is the olivine. So it's an SEM image done in backscatter mode. And so the melt comes in, reacts, and leaves olivine behind, eats up all the pyroxene that was in this layer. So the original interface was there. It reacted up to this point, and then in some cases it channelized. It made these channels where it had this core that was 100% melt, and then a dunite or olivine rim around it, and then here's the two-phase rock again. And you can see a second channel here. The problem in this case, so it's exactly this thing that we talked about. You have melt plus pyroxene plus olivine. You dissolve the pyroxene, precipitate out olivine, new olivine, and you have a chemically changed melt phase present. And the problem with this is this actually, we published this, and but some days there were like, we should publish this in the Journal of Irreproducible Results, because you could do it sometimes and it worked, and you do it another time and it wouldn't work. And we all have theories, all of us involved in this, which are quite a number of people, have theories about why it did or didn't work, but I'll be honest with you, it wasn't always reproducible. Yes?
So was your olivine and pyroxene rock air-filled at the start, or?
No. So these are done at, the samples are, they're synthetic samples. So we start with a powder of olivine and a powder of pyroxene, mix them together, and then we hot press them in a high pressure apparatus. And then these experiments are done in a high pressure apparatus. So there's, I'm not sure what you mean by.
But I'm just confused about what are the two fluids that are interacting to give you a surface tension that draws things up?
Oh, it's just that the melt would like in the first image I showed, a kind of sketch of a sample with melt along the triple junctions. So that's the capillarity part of it, that the melt would like to, the system is more stable if it can pull some melt into it, so just by capillary forces moves that melt into it. So there's no, in this case, in these samples, there was no melt in here at all. The melt simply gets pulled out of the source and moved into the rock. Am I not saying this well, maybe?
So the original fluid there was air, or,
Sorry?
I guess I'm repeating his question. What was there before the melt came in?
In here,
Yes.
2 phases, olivine, the lighter phase, and pyroxene, the darker phase.
Well, what about along the pores?
There
There was no.
There were no pores. There was no porosity in the rock ahead of time. I mean, there always is a tiny amount of porosity.
I was going to ask.
There's like one.
What do you measure olivine and peroxide out of? This from
They're made out of. So it's a good question. I mean, we grind up. There's a beautiful place in Arizona called San Carlos. That's on a Native American reservation, and they mine the olivine and the pyroxene, and they sell it for. Olivine is peridot, which is the August birthstone, and people like earrings and rings made from those things. So that's where it came from. We just grind it up, horrible things we do to it, and then we reconsolidate it. So the grain size in these samples is 5 microns roughly to start with, maybe a little bit bigger. Okay? Does that kind of answer the question?
So the invading fluid is creating the porosity.
Yes, the fluid is created. I'm sorry. Yes. Yeah. Good. Yes.
What's the temperature of the experiment?
In this case, I'm not 100% sure. It's either 1200 or 1250 centigrade. So, yeah. So it's high enough to melt the material down here, but not high enough to melt the rock.
Do you always get this 100% melt channel in the middle, like a dike?
Yeah.
But this is not predicted by the theory. Is it? This is not predicted when you are doing the calculations.
Why not?
I thought that you always have the porosity, but you never got 100%.
I think that's usually because the code breaks.
Are you talking about the Spiegelman simulations?
Yeah.
Will those lose validity at high porosity? The stuff should disaggregate and go to fluid.
I mean, who are you going to believe, the modelers or the experimentalists, you know?
There's a difference between the doses you see and the ones that are modeling.
Yeah. And I'll show you, there'll be, well, you can see pretty clearly here. I mean, if you look at it up close and personal, there is some CPX or some pyroxenes that come back out when you cool down, but they look dendritic in fashion, so you know that they were part of the melt when
Just
you were
a
there.
question about the reproducibility. Was it half the time it would work, or
Yeah, probably less than that. Yeah,
how much?
a third of the time.
All right.
Yeah. Enough that you kind of believe something's real in it. And maybe part of the answer to it will become clear in a couple minutes, okay?
Is there a volume change in this reaction?
Yes.
Which way?
I think that increases the volume a bit. I honestly don't know how much though, Dan.
I'm bothered about the pure melt channel. I haven't understood physically how that comes about.
Let's go ahead and maybe it will become a little bit clearer as I go ahead. If not, we can talk about it again. But there may be better examples where, well, we'll see. But then you'll have to explain to me what your concern is. Okay, so this is the setup. It's our normal, we would normally use this. Lars Hansen did his PhD thesis in this kind of assembly. But the two main parts are the center part here where the sample is. There's a furnace around the outside here that heats this thing. This all goes inside of a high pressure vessel. High pressure for us is around 300 megapascals confining pressure. And then at the top end, there's a tube or a hole that goes through all our pieces here that we normally would put a thermocouple in, but for these experiments we leave it open and it goes into a pore pressure monitoring system. So up here there's a volumeometer where you can back this piston off, and so if melt moves from here, showing the sample assembly, here's a source of reactive melt, a partially molten rock, and here's a porous sink. Right, so as melt moves from here, the source, through the rock into the sink. It pushes argon gas out of the sink up into here, and so the pressure would rise here, and the trick is you move this piston back to keep constant pressure up here. So you can control the pressure gradient. Pressure in the source is always 300 megapascals, but you can control the sink pressure between atmospheric pressure and 300 megapascals simply by moving this piston around. So we can monitor the pressure gradient and control the pressure gradient fairly precisely. Okay, so here again there's a setup. Here's the sample assembly, a melt source, a rock, which we're going to try to develop channels in, and then the melt accumulates up here in the sink, and there's the hot zone. And the experiments I'm going to tell you about today are all done between 1200 and 1250 degrees centigrade. So that's kind of the experimental setup. We're looking at the melt flow going through this piece here. Okay, so the starting materials, the porous sink is a piece of aluminum oxide, which has about 20% porosity in it. The partially molten rock is olivine, 50% olivine, 50% clinopyroxene. And we change or control the pyroxene content, and we've done 4, 10, and 20 volume percent melt. I'm sorry, this ratio is always 50-50, but we control the amount of melt in the starting rock. And the melt is a reactive melt. It's an alkali basalt. It's undersaturated in silica, that is in pyroxene. And we've doped that melt with a small amount of some heavy element. And we've used praseodymium, ytterbium, and so on. But something that you'll see later on is helpful when we try to look at X-ray scattering from the melt to try to map where the melt is. Okay, and what I need to point out is in Martha Daines' experiments that we just talked about, there was no melt here. In the experiments I'm going to tell you about today, there are two things that are different. One is that there's a pressure gradient between the source and the sink. That wasn't true in Martha's case. And we've put in, partially in the sample, we've added a small amount of melt so that we'd have some initial permeability between the source and the sink. All right, so there'd be some channels at the grain scale that went all the way through. Okay. So these are the starting materials. Not too much to show you here, but these are microprobe analyses showing sample with 4% melt, 10% melt, 20% melt, and this is the melt source. There were some solid particles in the melt source, so the red is the melt, the blue is the solid phases. There were some solid particles in the melt to start with, and you'll see those pop up when we move ahead a bit. This is again the sort of the starting material. These are X-ray maps done on the electron microprobe, and here you're looking primarily at aluminum, which tells you where the melt sits. Those channels. Here's the clinopyroxene shown in the calcium map, and the magnesium oxide map. You can see where the olivines are. So the system is pretty well dispersed. There's a little bit of melt spread around, sometimes in pockets. Most of the time, it's small triple junction containers. It's hard to get rid of the pockets completely. It's just a processing issue, but sometimes you get big melt pockets and it's hard to get them to go away. All right, so this is a pair of samples. This one was done, both of them were done with at 300 megapascals confining pressure, I think probably both 1200 degrees centigrade. Here's just exactly what you saw a moment ago. The source is here. This is the rock sample, the partially molten rock sample, and here's the sink, the porous alumina sink. In this case, there was no pressure gradient. In this case, there was a pressure gradient. And so you can tell, as soon as you pull the sample out of the assembly, you can tell whether or not the experiment produced channels. Because if it produced channels, the melt sink has been squeezed down, and that melt has gone, sorry, the melt source has been squeezed down, and that melt, you'll see in a moment, will appear up here in the sink. Okay, so it's a really indicative thing of whether or not the experiment did produce channels or not. So this is the case with no pressure gradient, and this is one of these examples I said where we didn't get channelization fully, even though it seemed like the possibility was there. And here's a case where there was a pressure gradient forcing the melt flow from Darcy flow from the source into the sink. So this is slicing halfway through that sample. So you saw this was the outside. This is the outside of the sample. The samples are jacketed in iron or nickel, and what you're seeing is a jacket, and it's just been color coded to show you that these are false color images, I guess, just to show you where the various parts are. This is kind of a center slice through a cylindrical sample, so you just take it and vertically slice it. Here's the sink, the sample, and here's the source of melt down below. There are some cracks that appear in it. Those cracks are all unloading cracks or cooling down cracks due to thermal expansion mismatches. You know that. I always ask my students, why do I know those are unloading cracks? Well, there's no melt in them. If they were cracked at high pressure, believe me, there would be melt in them. So they have to be unloading features. And this, so you can see here, this is the case where there was no pressure gradient, and looks like the melt source hasn't been squeezed down. Here's the case with the pressure gradient. You can see that the melt has been squeezed, deformed, so some of the melt's been squeezed out of that reservoir, and it's gone up here and it appeared in the sink. So porous alumina without melt looks to be white, and when you squeeze melt into it, it turns dark. Okay, so we know that there's been quite a bit of melt that's gone through here. And if you follow what goes on in the volume meter up the top here, you see you're squeezing along for a while, nothing much is happening, a little bit of melt might be getting through, and then suddenly there's this breakthrough, and that corresponds to when the first channel goes all the way from the bottom all the way to the top, and now there's a really high permeability path for pushing melt up through the sample. Okay. All right, so this is just kind of following the melt volume as a function of time, again using the volume meter. When you start having to back off this piston really quickly, it corresponds to when there's a lot of melt entering the sink and pushing the gas out of the sink up into the volume meter up there. Okay, so let's kind of dig down and take a look at what the samples look like. This is the sample where there's no pressure gradient. There's a nice reaction interface that I'll blow up and show you in more detail right here. So you can tell there's been some capillary driving of melt from the source into the sink. And this is the case when there was a pressure gradient, and there's much more rich in features. So the reaction layer in both cases. Again, we'll hone in on that in just a moment and look at it. But you can kind of see it, maybe if you've got good eyes right here. These channels that form. These are these finger-like instabilities that we've been talking about. And then below the channels, there's always a pot of olivine phenocrysts that are large olivine grains, most of which were in the melt to start with, but which have kind of flowed up. As the melt flows here, the olivine gets entrained in the flow and basically doesn't Darcy settle out of the system. And then occasionally, not occasionally, frequently you'll see just the olivine phenocryst at the bottom with no melt channel associated with it. So here you can see the phenocrysts, the olivine grains are associated with a channel. Here they're associated with a channel. This just means that there's a channel in the third dimension that we haven't intersected. So either out here that we polished away, or behind the screen that we haven't gotten to yet, there's a channel. But those phenocrysts are always associated with channels, and you'll see why we know that in just a minute. All right, this is just one more example. Here's a big pile of phenocrysts, and there should be a channel, and you don't see it, but it's there. It just isn't obvious at this point. And one minor point I wanted to point out, so these samples were done with a starting melt fraction of 20%. This one has 4%. And it seems to be a robust characteristic that if you have smaller amount of melt in the rock source, or the rock that you're invading with melt, the channels tend to be more narrow and longer, so they have a higher aspect ratio. You kind of see that here, that they're kind of fat little guys here, and this guy's just this long. And I think that's a fairly robust observation. Okay. So this...
Are the channels tubes or plates?
Tubes. Yeah.
And does the phenocryst region correspond with the size of the channels, the length or the diameter?
No. You'll see this, we'll come back to this and you'll see it in a minute, but no, the phenocryst, I mean, that's a really good question, and I think the answer is correctly no, that doesn't seem to be a correlation. But I'm not 100% sure of that. I don't know that we've done enough statistics to actually say that confidently or not. Okay, so this is a picture of the reaction layer. The basic point here, there's a time step from 150 minutes to 300 minutes. Oops, sorry. And there's a temperature step from 1200 degrees to 1250 degrees centigrade. And you shouldn't pay much attention to the fact it's a different melt fraction, but you can if you want. But you can see the time step that the reaction layer gets thicker with increasing time. Okay, so this is no fingers around here. And this is if you go to higher temperature and you have a bit more melt. You can see that, again, as you increase time, the reaction layer gets larger with increasing time. And you get more melt accumulating in the reaction layer as time goes on. And the higher temperature one also has more melt, and the reaction layer grows faster at higher temperatures. So there's a time effect, as you would expect for a diffusion control process, and there's a temperature effect that affects the amount of melt that's present in the system. All the grains down here, I'll tell you, they're all olivine. All right, the pyroxene is totally gone. These are all olivine grains. Here's the two-phase material. Up here, you can see the darker olivine grains sitting up here. Anyhow, so this is a two-phase rock. It has a small amount of melt in it. This is the part, here's the melt, full melt down here, and this part's been reacted. The pyroxenes have been eaten out here. They're totally gone, and you're left just with olivine. Okay, so this is just a close-in view. Again, it's this melt plus pyroxene plus olivine that you start with, and it reacts and makes melt, the second melt phase, and leaves behind olivine. Here's the reaction layer for the sample that I showed you on the left-hand side in the previous case. And these are all olivine. They have some reaction rims around the outside, which is iron enrichment, which is the melt has more iron in it than the grains do, so when you grow additional material on the outside, it's a little bit iron-rich. These are all done in backscattered electrons, so bright means heavy, dark means lighter elements. And so this, if you look down here, it's hard to find any pyroxene. If you look up right at the reaction room, so right up here, this is this piece right here. So right at the reaction room, you'll find some pyroxenes growing in the system that eventually get dissolved back out, and you'll here is sort of a quench crystal of a dendritic form of clinopyroxene. Okay. And you can measure the reaction right there. Some nice work done by Morgan and Liang. Oh, sorry. A few years ago, where they looked at the reaction rate kinetics and argued that it was diffusion limited because it followed a layer thickness, a layer thickness versus square root of time linear dependence in that space. Again, we used Win-Lu's permeability law, calculated what the initial permeability was. It changes as a function of melt fraction. Right? The more melt, the more permeable the system. And then you can see that things are changing dynamically in the system. This is the olivine grain size in the reaction layer. It's getting bigger as time goes on, so this grain size is a function of time. And this is the case of melt fraction, and the melt fraction increases, which is what you could see back here already, that the melt fraction from here to here has increased quite a bit as a function of time. Okay. All right, so those are some of the characteristics. This is going to now get to be important. The solid symbols are samples, represent samples that did not form fingers going through the system. And the open symbols are ones that form fingers, okay? And so you're going to see that where it's going to come up again and again. The diamond, squares, and circles are different melt fractions from 4% to 20% melt. The colors are two different temperatures. 1200 degrees is a bit colder than 1250, so 1200 got to be blue, 1250 red. So the shape of the symbols is the melt fraction, but the filled versus open means the filled ones did not produce fingers, the open ones did. All right. All right, so there's the change in permeability. So when you're trying to design an experiment, none of these parameters are constant. So this is where, for us, having people doing numerical experiments on these things are really important, because we can model, or we can calculate simple permeability if the melt fraction is fixed, but as it evolves, it takes a more sophisticated calculation than we typically would do. Okay, so this is a couple of optical micrographs, a sample that didn't produce a finger, a sample that did. Here you can see kind of more detailed the size of these are basically olivine grains that sat in the alkalite basalt before the experiment. They get entrained in the melt flow and come up along the channels. This is a plot of the settling velocity calculated using Stokes' law for those grains as a function of grain size, which gives us some idea what the melt flow velocity has to be just to keep those grains floating up there and staying up on top. They should settle down. You can see here, when there's no melt flow, the big grains are at the bottom. When there is melt flow, the big grains are sitting up at top. Okay. A few always escape to the bottom, but most of them sit up at the top of the system. So the settling velocities should be on the order of a micron a second or so. If you make a plot of melt velocity, which you calculate using Darcy's law as a function of pressure gradient, and then this becomes kind of the first insight into when you make fingers and when you don't make fingers. And you can see, it's not totally completely clear, but it looks like anytime the velocity is below about a micron a second, you don't make fingers. And when the velocities are higher, you make fingers. So either you have a high pressure gradient to make the velocity high, or you have a high temperature to make the velocity high. So it looks like this is going to turn out to probably be the best scaling that we have, is that if you're flowing at a velocity greater than a micron a second, then, which is 10 meters a year or 20 meters a year or something, then you make fingers. So the open symbols again are the ones with fingers. The closed ones are samples that didn't make fingers. So here's what these channels look like in more detail. So the melt is just down off of the screen. You can see the reaction layer here. And you can see some of these large phenocrysts, which are being advected up into the channel. Maybe it's easiest if we start over here. You can see here there's a melt channel, really 100% melt, no grains. Anything you see, these small guys are all dendrites, so they've crystallized out of the melt phase. And then it looks like the channel is kind of getting pinched off at the bottom, and maybe gets pinched off here. And this is a little bit hard to tell exactly what's going on. I'll try to give you a bit better picture in a moment, but this probably is a finger that kind of goes into the screen and comes back out. So it's a crooked finger, not just a straight finger. But it's possible that these guys get pinched off and then have to rise on their own. And again, you can see some of the large grains that came from the meltdown here, these phenocrysts, and get entrained and come out and appear up in the flow up here. Just like the reaction layer, what's in this channel, these are olivine grains that you see here, the dark guys, and then plus melt. So all that's up here is olivine plus melt, but here there is this kind of elliptical shaped bit of melt that sits in this channel down here. Okay, so that's what the channels look like. You can do the chemistry on these things, and this are chemical maps. I'm just going to focus on a couple of these. I don't remember the order I did these in. So look, so this is calcium and iron melt. So calcium is a main component in the pyroxene, and you can see that there's no pyroxene, no calcium sitting in this reaction layer. So this is the reaction layer, kind of continues up in here. This is the melt. It's a bit richer in pyroxene, which is not surprising since it was made by dissolving pyroxene into the original melt. So this becomes melt 2. Melt 1 is out here. And the yellow guys are the pyroxenes that haven't been attacked by melt yet, so they're further up in the sample. So you can see that there's a change in the calcium content in the melt phase. Here's the iron map, which is basically mapping the olivine. So all this lighter blue stuff is olivine that was made by the reaction. The darker blue, or the sort of somewhat lighter blue, but the darker than here, but these guys, really dark guys, are the pyroxenes, and that blue are the olivines. And so there's been a chemical change. These guys, these phenocrysts in the melt are, in the mole fraction wise, are 70, or say they're 22% iron. The olivines in here are 18% iron, and the olivines in here are 12% iron. So these are more iron rich. The melt, when the second olivine gets created, gets dissolved in the melt and precipitated out as a more iron-rich olivine. All right, and this is maybe the most important one in terms of what we've been saying. This is the silica map. So here's the melt that started. You can see that the melt up here, it has more silica in it. It's moved up the scale from up to about there, from starting down in here somewhere. And that's exactly what we said, right? As you dissolve the melt is hungry for pyroxene, and pyroxene is silica rich. So the melt should become silica rich, which it does. So the dissolution process takes the pyroxenes, puts it into the melt, makes the melt more silica rich, and leaves this melt plus olivine room around the outside. This just what this plot shows, calcium enrichment in the melt. So this is a plot of the melt composition normalized by the composition of the source, of the starting melt composition. And you can see that the melt in the reaction layer becomes richer in calcium, as I just said. It becomes a little bit richer in aluminum, and it becomes quite a bit richer in silica. All right. It becomes depleted in magnesium because it's precipitating olivine, and the magnesium goes into the olivine. So this is the olivine showing up, and this is the eating up the channels to put more silica in the melt phase. Okay, so we did some X-ray tomography, kind of low resolution, very low resolution X-ray tomography, but something we could do at the university. Let's see. Now I see why this is hard to do. Okay. So I'm going to show you this. This is a serial section coming up through the sample. I'm going to primarily focus your attention on this one up here, which is looking down on the melt as it's coming up at you. But there are some features you can see in here. You'll see melt channels cutting through. So the light stuff is melt, right? And the darker part is the rock, okay? And the melt, you see the melt, these are done by X-ray attenuation, and you see the melt because of the heavy element, praseodymium or something that was put into the melt, okay? Or terbium, I think, in some cases. Okay, so that's why the melt appears lighter. Otherwise, it would be difficult to do this experiment, or this analysis. Oops, sorry. Got to push on this somehow. Did I do it? Oh, don't tell me you're not going to get to see the video. Okay, well, there it goes. I just had to be more patient. Oh, it only goes on my machine. Aha. Help, Lars. Can I throw it over here? Yeah, I did it. Thank you, Lars. Lars was showing me how to do this stuff earlier. So now, of course, I have to look over here. So let's look at the one up here. And you see pores coming through. You see these white regions, which are kind of migrating their way up toward the surface. And I'll take you through it one more time when we get to the end of this and just kind of show you the olivine pods. But you can see the pores at this interface that were gases trapped in the melt phase. And there you can see one channel that kind of shot up from the side. So let me do it one more time. Okay, so this is crazy. All right, so you see the white guys. Let me back this up just for a second. Yeah, show you two other things. See if I can stop this quickly enough. All right, so there's the interface, and see the white around up there and here. Those are the olivine phenocrysts that are at the bottom. Okay, so you're sitting right at the bottom, right at the melt source interface. And these are the big piles of olivine phenocrysts. These are pores that were in the melt phase. They exalt from the melt and then buoyantly rise and sit right at the interface between the melt source, which is here, and the sample, which is here. And the sink is up here. Okay.
What are the black dots?
Black dots are pores. They're just in the gas phase when you melt or in the melt phase. There's always some gas trapped in it. Okay. And then as you go up through, you can begin to see channels form. You can kind of see them coming and going as they're kind of wiggling around back and forth. And at the end here, you'll be able to see one channel that's kind of shooting through this section, going from the bottom up to the top. And you see it come in here. You just get into the right plane that you can see it, and you can see the big olivine phenocryst pile at the bottom. All right, onward. Now I gotta close this. All right. Anyhow, so that's kind of what they look like. This is kind of just a rendering of what you saw before. A zero pressure gradient, long time experiment. No channels formed. Here's the melt source. This is the sample, and the sink has been removed at the top. So the red melt has been highlighted in red, and you can kind of get some idea of the morphology. And we just simply don't have the resolution to know, is this really a disconnection that occurred or not? It may well be there and that we're just not able to resolve it. And you can see here are some more well-developed channels of the type that you saw in the video a moment ago. Okay, so you can see lots of them. Some of them made it part way up, some of them made it all the way through. Here's another kind of image of the same thing. This is looking from the top down with the channels kind of coming up at you. And this is a side view that we saw before, the source, the sink, and the sample in between. So they're basically tubular kind of structures. They're not simple tubes. They kind of have branches and things that go on them, but they're two-dimensional. They're tubular more than, and they're certainly never planar kind of features. This is one more example, just kind of showing you an X-ray tomography where you can see what we just saw. Here's the melt. There are the bubbles at the interface. Here's the phenocryst pile sitting below one of the large channels going up, and the melt sink is up here.
What's the melt content in the partial molten rock?
Sorry?
What's the melt content in the partial molten rock?
I'm going to guess, and it partly is a guess, it's 10%. It's either 4, 10, or 20, and I think that was a 10% sample, but I wouldn't swear to it.
Do you find the same type of channels forming in the 4% one?
Yeah. Yeah, the only thing in the 4% one is that they tend to be more narrow. They don't tend to broaden out as far. They tend to be more focused. When you get done, about 2% of the sample is made up of channels. And this is just a plot of the volume of melt that's present versus the length of the channel. And so the longest channels that go all the way, so this is a channel that made it all the way through the sample. There's the sample length, and it gets up around 2% of the melt gets to be in it. So it's a fairly focused delivery of the melt system. And this is one thing that we had hoped to actually, we're trying to figure what things can we actually measure that are easily relate back to the Dom-Kohler number and the Peckley number. And so one is channel spacing. And it turns out channel spacing is kind of fixed, always between about 2 and 4 millimeters apart. This is, again, the same code. The red ones are the high temperature, blue ones are the lower temperature, and different melt fractions. And this is just plotted as a function of pressure gradient. But you can see that they're all around 2 or 3 microns in size. And you'll see why that might be the case in just a moment. This is just to remind you of Spiegelman's plot of Dom-Kohler number versus Peckley number for this problem. And I kind of pointed out this line before, and basically you see along this line, I forget, somebody counted the number of nucleations, but there's something like 11, I guess, channels that appear in each of these cases, which is, and this line is constant, if you like, Dom-Kohler number times Peckley number. It's always 1600 along this line. So maybe that's important. Here's our results plotted as Dom-Kohler number, so in the same space, Dom-Kohler number versus Peckley number. And all of our samples, these are all the experiments that we did. And using this kind of plot, again, the solid symbols are samples that didn't form in channels. The open symbols are ones that did. There's kind of a propensity of samples to be down in this region. Just to put it back on the scale of the previous plot from Spiegelman paper, here's Dom-Kohler number times Peckley number. And you can see the range of values so this is a log scale over here. This is a linear scale. So maybe we can change that product by a factor of 2 or so, but that's about it. So all of our experiments tend to sit in here, but you can see the propensity is to have the lower temperature samples not forming channels sitting down below here, but you can see there are some that form channels sitting right underneath it. And it tends to be out here at higher pressure gradients, faster Darcy velocities, that we tend to get channel formation. Okay. And this is just to remind you the figure I showed before, that the best correlation we've been able to find is that if you exceed a critical velocity for the melt velocity, you tend to form channels. At lower velocities, you tend not to form channels. Okay, just some summaries. we're able to make channels, they have olivine and melt in them, which increases the bulk permeability, so you get really rapid flux and melt through the system. And one important point, at least from the experimentalists, is that it's really hard for us to get a wide range of this combination of Dom-Kohler number times Peckley number. If you increase one thing, you decrease the other thing, and too many of the physical parameters are interconnected. If you want to make the melt more reactive, you change its viscosity, and you have to take into account all those changes. And the melt morphology, and this is where I'd like to kind of end for right now, is that the melt morphology is like fingers or channels going through that are tubular in shape. The crooked fingers they tend not to be straight. They don't just go straight up, but they have some motion in the third dimension. And they're not tabular, such as the structures found in ophiolites. So, and that's what I hope to talk about in the next talk, is what does deformation do to change this perspective. Oh, yes. That was it. I forgot I had that. All right, so there's this picture. All right, thank you.
So we have some time for questions.
Can you estimate compaction lengths in the partially molten sample?
Yes, and I don't honestly remember, but it's on the order of the size of these samples. So it's less than a centimeter, but it's on that order. But I don't have that number fresh in my mind. I should have, but I avoided saying compaction length the whole time. Bam.
Well, can you say a little bit more about the composition of the alkali basalt that you used? Where did it come from?
It's a Hawaiian. I don't know off the top of my head. It's a Hawaiian, I think, 1850 flow, and I can tell you.
Lower. From Wanaloa or from Alamama?
I don't know. Okay, but I can tell you.
The thing which is worrying me is whether what you're looking at is actually not a reactive instability, but Sackman-Taylor instability.
Okay.
Because the viscosity contrast between alkali basalt and the melt you'll make from olivine and clinopyroxene is large, and it's exactly the right way around to produce fingers.
Okay. So you and I need to talk more.
So just one clarification: the melt in your partially molten rock is the same composition as, or you add the same basalt?
Yes. Yeah. But because it's reactive, it's reacted already. So the melt that's in the rock is clearly a different composition when you start the experiment than the melt from the source. Yeah.
The silicon that matters.
Right, so I was going to ask along the same lines, if you do the same experiment with orthopyroxene instead of clinopyroxene, I mean, what was the reason for using clinopyroxene instead of, if it's just the silica?
Let's see, we went to the cabinet, and in the cabinet there were 2 bottles of powder. We could have done it with orthopyroxene. In fact, Mate has done some experiments with orthopyroxene, but none yet in this configuration where he has a pressure grid. And he's done quite a number, just looking at the Martha Daines type experiment with just using capillarity to draw the melt in. Martha's experiments were done with orthopyroxene and with a MORB, mid-ocean ridge basalt. Right?
One of the things that surprises me is the way the channels, once they're formed, are moving about. Whereas the basic mechanism for forming channels would lead you to suggest once you've got one, it will just stay there and get bigger.
Rather than expanding upward, I mean, or they're not moving about.
They're moving side to side.
I don't think they're necessarily moving side to side. I actually have no way of knowing if that's the case, but my assumption is that the finger goes up and then it curves over and then it comes back. So it's not. Well, maybe that's what you're saying. It's not like the channel gets there and then it's able to move side to side, but it doesn't go directly upward. But again, you have to remember gravity is not very important in this problem. And so it's following chemistry. So it looks over here and it says, well, there's a little more pyroxene over here, and I'd like to have that pyroxene, so it will follow the heterogeneities in the sample, if nothing else.
I mean, there are 2 things. One, just to clarify that question, you don't actually have
the time evolution of a single sample. Is that correct?
That is correct.
You have to
It's a,
stop the experiment.
you stop the experiment, you cut it up and do nasty things to it so you can analyze it. And maybe Win-Lu can do a non-destructive, maybe we can do one in the synchrotron or something. But no, it's not a live experiment.
And then the second question, can you say anything about the porosity in the regions that are not channelized and whether that's changed? Has there been any compaction, for instance?
No. If you look away from, let me see if I can find a picture really quickly. Yeah, so if you looked over here, over some scale length about that distance, there might be a small amount increase in melt, but if you looked here, there's not.
One last question maybe for coffee? No? Okay, well, why don't we break now, drink coffee for a half hour, chat more, and then we'll come back in here. Good? Thank you.